thermalization and Schrodinger cats.
Okay. Yeah, so I'm going to tell you about an interesting, well, I think it's an interesting little example that we have worked out recently. Okay, and so what this, so these are two students who have been working with me at Princeton. So what I'm going to talk about is closed quantum many-body system. And what do I mean by closed? What I mean is, it's a quantum system, many degrees of freedom. In particular, it's going to be a spin system. And closed means it's isolated from the environment, so its dynamics is just given by its Hamiltonian. No coupling to a heat bath. Okay? That's what we mean by closed. And this has become a big topic of interest recently basically because of experimental developments in physics, because people the atomic physicists have started doing many-body physics, because the atomic physicists, they can cool down lots of atoms and they can put them all together in a trap, and they're isolated from the environment and interacting strongly with each other. They can tune the interactions. So this has become something that's a very, very active subject theoretically and experimentally. And it's also motivated by dreams of quantum computers, where again a quantum computer, at least some designs of quantum computer, are closed, at least some of the time, closed many-body systems, a bunch of qubits interacting with each other in some way. Although usually they're not really closed because you're manipulating them. Okay, but the issues I'm going to be talking about here are the issue of thermalization, and I'll say, well, I'll just use a little bit of what I mean by that in the particular example, but maybe at the end we can talk more generally about thermalization if people want to. And what I actually am going to be looking at is the combination of thermalization and phase transitions, so symmetry breaking, spontaneous symmetry breaking due to phase transitions. So it's sort of these two together playing out in a closed quantum mechanical many-body system. Okay, so that's sort of the setting. Okay, and I'm just going to go to one specific model just to show which shows some interesting things. It's a textbook model, but I'm going to be asking questions that I think are not asked in the textbooks, at least the ones I'm aware of. Okay, so I'm just going to look at the mean field, meaning every spin coupled to every spin, transverse field, Ising ferromagnet. Right, all these words have meanings, and I'll point them out. So here's the Hamiltonian. Okay, so what I'm going to do is I'm going to look at a particular Hamiltonian, and then I'm going to modify, which is that model, but it doesn't thermalize. And then I'm going to add a perturbation to make it thermalize. So first, I'm going to write down the model H naught, which I'm later going to modify just a little bit. Okay, and what it is, okay, so we have spins, and I'm going to call them little si, which is a vector spin a half of a Pauli matrix, right? So that's just my normalization right now. Okay, so we're going to have a coupling. Okay, I less than j equals 1 to n. So we're going to have n spins, and their z components are going to be coupled to each other. That's the Ising ZZ couplings. Okay, mean field. Everybody's coupled to everybody, and we've normalized the interaction by 1 over n, so there's a proper thermodynamic limit. Okay, and then we got to add the transverse field, minus gamma, sum I equals 1 to n SIX. Okay, that's the transverse field. The ferromagnet is the minus sign here, So the interactions, lowest energy, the spins are aligned. Okay? Very simple model. And this is a parameter generally, but just for today, I want to work in the regime. Okay, so what does this model do? If gamma is small and I go to low temperatures, the spins align to get the lowest energy. If gamma is big, the spins point along the x-axis and the z components of the spins don't align. That's the ferromagnetic phase. I want to be in a regime where at low temperatures this guy wins, but this guy is still non-zero. And in particular, just to pick a number rather than look at the whole phase diagram, I'm going to take gamma equals a quarter. So that's right in the middle of the phase where gamma is big enough so we have strong quantum effects due to this term, but small enough so the ground state is a ferromagnet. Okay? We've looked more, there's a whole phase diagram, but today I don't want to go into that. Okay, so this model has symmetries. Okay, so symmetries, has a lot of symmetries. It's integrable. It has the symmetries, all permutations of the labels on the spins, right? Any permutation of the labels on the spins, it's invariant. Okay, so that's one symmetry. And then it has another symmetry, which is global spin flip. And in particular, a pi rotation of every spin about the x-axis. So that operate, I'll just call it G, product I equals 1 to n sigma I x. Okay. So this operator, which flips all the spins by rotating them by pi about the x-axis, this commutes with this Hamiltonian. This is the symmetry that's spontaneously broken when it orders into a ferromagnet. It's this symmetry that's broken. This model in particular, because it's everybody interacting equally with everybody else, also has all these symmetries of the full permutation group of n objects.
G and H0 commute or what?
Yeah, right. So G, in fact, so G commutes with H. Okay, I'm going to change H. So what I'm going to do, first I'm going to talk about the dynamics of this model, and then I'm going to perturb it to break all these symmetries but keep this one. Okay, so G commutes with H. And right now, H naught is invariant under all those symmetries as well. Right? Okay. Clear?
I guess you haven't yet defined H. I mean, H naught over there.
Yeah, right. Yeah, this is true for H naught as well. It's true with the naught there, and it's true when I take away the naught. It's still going to be true, right? Actually, let me just put the naught there, and I'll just take it away later, just to make it very clear and precise. Okay. Now this model it's a mean field model. It's simple, right? And how do you solve it? Okay. First of all, you define the total spin, big S. So that's a capital S. Sum over I equals 1 to n of little s I. Right? And then we can just write the Hamiltonian in terms of that variable. So H naught is minus 1 over 2n big S z all squared minus gamma big S x, and then actually plus 1/8 to be precise. But this is just a constant, so it doesn't matter. This the square of this, which is the magnitude of the total spin, s squared, also commutes with H naught. Right? It's obvious, right? If H naught can be written this way, right? If I just write this out and write out sigma z as the sum and square it, I get all these terms, right? Okay. So since this just consists of total sz and total sx, that's the only operator content in here. Both of them commute with the magnitude s squared of the total spin. So total spin magnitude is conserved. None of the individual components are conserved, just the magnitude of the total, right? Okay. But that, and then when we do a large system, these spins are large, SZ, SX, the total spin is large, and the fact that SZ and SX don't commute is a tiny correction, and so we can take a classical limit and just at least for the thermodynamics, ignore that these are operators and don't commute with one another. Okay, for the dynamics, we have to include that fact. Okay.
So let's say, just to be
Okay.
clear for some people, spin systems, quantum spin systems, this is acting on C2 to tensor.
C2 to the n.
C2 to
Right.
the n.
So each spin has a two-dimensional Hilbert space, and the full many-body Hilbert space. When we say many-body Hilbert space, what we mean is an outer product, tensor product of all those Hilbert spaces of all the spins. Right. So, right. C2. Is that right?
Well, we usually write tensor.
Yeah, right.
It's a tensor
Right.
outside. Yeah. There you go. That's more familiar.
Right. Okay. Yeah. He said C2, didn't he?
C2. It should be C2.
He raised the two.
Oh, raise the two. But he told me to do it at a low level. That's what he said at the beginning. So I'm only going to use subscripts.
This is the kind of low level stuff I'm asking you to say. And then the Pauli spin matrices just act on that by the usual fashion.
Yeah. Right. So the operators are tensor products of Pauli operators for all the spins. And so this operator here is the tensor product of the identity on every other spin and the sigma x Pauli operator on spin I, to be precise. Okay. So this is a textbook thing. People can solve for the phase transition, do the thermodynamics of this, but what I want to do actually is the dynamics, okay? Which you normally, the dynamics of highly excited states, which is not often looked at, and so that's what I'm going to do today. So we focus on the dynamics of this in highly excited states.
So is this related to this is also related to the classical Ising model, right, or not?
Well, normally you wouldn't have a transverse field on the classical Ising model. This thing gives it dynamics because, right, actually I shouldn't have emphasized, of course, for the thermodynamics of this, the fact that Sx and Sz do not commute is not important, but for the dynamics it is, right? And I'm going to actually focus on the dynamics, right? And so, and the classical Ising model doesn't have dynamics, right? So I'm going to be focused on the dynamics. So in that sense, it's issues that just aren't there in the classical Ising model, okay? You know, well, there'll be some thermodynamics as well, but the focus is on the dynamics, okay? Right. And these operators, S, X, they're of order n, right? I'm going to take, you know, we have n spins. We want to ultimately take n to infinity to see phase transitions. So these operators are all, you know, we're talking about a big spin. This total spin is of magnitude order n. It's a large spin.
All spins appear between 0 and n/2.
That's right.
But
That's right.
if you look at the ferromagnet, the ground state wants to be a big spin.
That's right. Yeah. So I'll be, yeah, right. Of course, you can have total spin 0, but I'm not. That's a tiny bit of the Hilbert space, and that's not going to play an important role in the regime I'm talking about. And so we'll be looking at spins that are of order n. Okay. So what does the dynamics of this system look like? And we can actually do a semiclassical dynamics. Let me just list the dictionary here. So semiclassics for this. So we take Sx is like the position. So the dynamics of this model we can think of as a particle moving in a potential, right? Just to make it familiar like semiclassics. So Sz is the position. Okay, so that this here ends up being the potential energy when we do semiclassics. Right? Now Sx, what does Sx do? Sx is an operator which changes Sz by increasing it by 1 or decreasing it by 1. So this is the kinetic energy operator here. So S minus gamma Sx is the kinetic energy when we do the semiclassics. And incidentally, Sy is like the momentum, sort of. Okay.
So do you really have to do semiclassics, or is it just something you do?
Well, I'm going to present what I'm going to tell you today using semiclassics. I'm not going to insist you have to do it that way. But yeah. Right, this is an integrable model. I'm sure there's lots of ways of solving it, as is usual with integrable models. But I'm going to break the integrability, so I want a simple reference picture that I can then perturb. And for me, this is semiclassics is the nice one. Okay, so let me just draw a diagram of this. Okay, so what we're going to have is I'm going to put energy on the vertical, or the energy, and then so Sz is the position, so we'll put Sz on the horizontal. That's okay, yeah. So Sz on the horizontal. Okay, so let's say and let's say at a given magnitude of the total spin S, which with this h naught, that's a conserved quantity. So I can fix the total spin S and look at what does the dynamics look like. Okay? Here's the energy. Here's the position. If you're going to do dynamics, first of all, you should draw the potential energy in. Potential energy is just quadratic. Okay? So it just goes like this. Potential energy is quadratic. So this is the potential energy. Okay? And it goes out to S over 2. That's the biggest you can bring out to S, out to plus S. Right, S is less than or equal to n over 2. Right, and it's of order n. Okay, so Sz can run up to plus S, and of course it can run down to minus S. Right? So that's the potential energy. Now this is the kinetic energy. Right? What does this operator do? It just hops. Right, Sx operating on Sz equals m gives some Klebs-Gordon coefficient, which I'm not going to say. Let's just say, C1 m plus 1 plus C2 m minus 1. Right, that's what Sx does. And these coefficients are simple numbers, but I didn't prepare that, and I don't want to write them because I'll write them incorrectly. But they're standard. That's in textbooks, of course. Okay. And this has got a minus sign on it, and the ground state of this kinetic energy.
You just change the conventions.
Have I?
Yeah, because you had S equals 1/2 Pauli matrices. So I guess the magnetic quantum.
This is a capital S. These are uppercase S's, so that's this operator.
Oh, okay.
Right? This was a lowercase s.
Yes. No, okay.
Sorry. Sorry, my typography might be unclear. Okay, but anyways, the kinetic energy is an operator unlike momentum, 1/2 mv squared, which is positive definite. This is a kinetic energy operator that runs in a band, right? We're talking about a particle hopping along this axis, with a kinetic energy like this, which can be negative or positive. And so there's a band, and the bandwidth is given by Sx, the biggest Sx can be, right? If we're at Sz equals 0, Sx can run all the way up to S and down to minus S. So there's a bandwidth like this, right? That if I fix Sz equals 0, Sx can run anywhere from minus S to plus S. And the kinetic energy can run anywhere from minus gamma s to plus gamma s. And all these states are available. You know, there's two. And so it's just like a particle hopping in a band in a tight binding model. And as you go out to larger SZ, the range of Sx that's available, right, we have Sx squared plus Sz squared is less than or equal to S squared, right? Because, of course, we add, right, actually, SS plus 1 to be precise. So this band gets narrower as you go out to the ends here. And you get something which, for certain values of gamma and S, looks like this. Okay, so this is a band. So and this is the bottom of the band, which corresponds to Sy equals 0. So this curve I've drawn here is just this as an equality. Right? If I set this as an equality, it means Sy is 0. It means the particle's not moving because Sy is the momentum. And that's this shape here. Right? Okay. And if we take a point in the middle here, like here, Sz has this value. Sx has a certain value that puts it here. And Sy has a value given by, right, I can just say this, Sy squared plus S squared plus Sc squared equals Ss plus 1. And so that sets Sy squared. And there's two possible values. Either Sy is positive and it's going that way, or Sy is negative and it's going that way. And that's just the spin precessing. Okay? Okay, so this is a picture. And what we're going to be interested in is the ferromagnetic phase of this system, where the energy is below. Here, let me just get another color here. The energy is below this here. So we have these low points at low energy here, and then there's a barrier, right? So let me draw a line here. That's hardly any different color, but so draw a line there. Okay, so let's say we're at this energy, right? So this energy is classically allowed to be in this region. This is where Sy squared is positive, and over here. And what the system is going to be doing if you put it here at this energy, say in this well, think of Sy going in and out of the board, it's going to be doing an orbit precessing around like this, which is just all these spins precessing around the mean field. The mean field due to the other spins as well as the field due to the transverse field. And if you put it over here with a negative Sc, it'll precess here, right? And it precesses, so this is spin precession, and the rate is of order 1, right? Because the
Can you tell us more precisely what the dynamics is in the spin precession?
Because he wants you to write down an equation of motion, Heisenberg equation of motion.
Heisenberg equation of motion, yes. Well, the spin is just going to precess around the mean field, right? So the mean field is, so the mean field, right, is minus Sz over n minus gamma, right? That's derivative with respect to gamma. Sorry, this is along the z direction. This is along the x direction, right? So that's the mean field at any one time. And if the spin is not parallel or anti-parallel to this field, it will precess around that field at a frequency given by the strength of the field. And the strength of the field is of order 1 because Sz is of order n, so this is of order 1, and gamma is a quarter. So the spin is precessing, instantaneously it's precessing about the mean field. It's not simply precessing about the mean field because as it precesses, the mean field changes. So it's not a perfectly circular precession, the orbit. Yeah. Yeah.
I guess the two-dimensional sphere is a symplectic space for those who prefer the Slavich, right? In effect, this is the Hamiltonian flow.
Yes, exactly. Exactly. So there's a surface. So I've drawn, there is a surface which at sy equals 0 has this edge, and it comes out like this, and it goes in behind, and it's given by this equation. And the dynamics is conserving energy. Semiclassical dynamics conserves energy, and it just does orbits going around like this. If it's up here, they go around like this. I might have it the wrong way around. It goes one way or the other, definitely, but there's a convention.
If you write the gravitational relation, you can interpret
Yeah.
them as a Poisson bracket in effect.
Exactly, exactly.
Yeah, why do you
For
say
every n, you can solve the equations of motion.
Exactly.
Just fix the total spin
Yes.
to be given
Yes.
and then look at there is a single spin dynamics.
Yes, this is simple, at least to many of us.
yeah, I mean,
I'm not trying to pretend it's not simple.
Why do
I'm
you
just
say-
going to make it more complicated later.
why do you say semi-classical instead of state quantum?
Well, okay, so no, the way I'm describing it is not straight quantum, right? I'm saying it's on this surface and it's going around in an orbit, and I'm going to say it tunnels through this barrier. That's semi-classical discussions. Of course, that's what happens physically, quantum mechanically as well. Yes. But I guess I'm not.
Classical in the sense that you can simultaneously talk about values of
Yeah.
different components.
Right. If you really wanted to do the quantum thing, then it would be a wave packet concentrated near this surface, which was going around. Right. Okay. So we've got this spin precession in here or in here. So if my spin system is over here or over here, it will precess around at a rate of order 1. Okay? But then it's coming up to this barrier, at rate of order 1 and making attempts to tunnel, right? And so it tunnels across this barrier, which is of a height of order n and a width of order n, so it's an extensive barrier. So it tunnels with rate exponential minus some coefficient order 1 times n. Right? And this tunneling rate, so one can do a semi-classical or what we call WKB analysis in physics to get the exact dynamics here and to get the exact probability of tunneling through here. What's the rate at which it will tunnel through this barrier from up to down, right? So the macroscopic magnetization can be up or down, and it can flip. But it flips at an exponentially small rate. Okay? So the eigenstates of this, so if I fix S and I solve this quantum problem, it will have, right? So if S is, I have a given S, SZ runs from, SZ runs from minus S to S by integers. So there are 2 S plus 1 states for a given S. And so there would be 2s plus 1 eigenstates at which you have eigenvalues in here. And they range over an energy which runs basically from minus gamma s to plus gamma s. So it runs from a width of order s. So the level spacing of the spectrum of H naught, actually write it this way, spectrum of H naught is of order 1. And that's reflecting, this spin precession at order 1 is basically just this level spacing giving the spin precession. Okay, so that's one statement. For in the ferromagnetic phase, so these eigenstates for energy less than this barrier, which is gamma s, are, well, what do they look like? They look like this, 1 over root 2 up. Let me just give it a label n, plus or minus down. Right, so this thing is symmetric under flipping SZ. That's this symmetry operation here. There's no degeneracies. All the eigenstates will be simultaneously eigenstates of H naught and global spin flip. This is an idempotent operator, so it has two the states are all either even or odd under spin flip, and so they look like this, right? And so this is what people often call a Schrodinger cat state, because you've got a coherent linear combination of two macroscopically different states. So think of this as the cat alive, and this is the cat dead. And that's what all the eigenstates look like if we fix S like this. Actually, that's what they all look like. Okay. Good. And then we have a degeneracy. So for a fixed S less than n over 2, there are many ways of taking n spin a halves and adding them up to make total spin S. And the degeneracy, I'll just call it G of S, and it's just the binomial entropy, or the Shannon entropy, whatever you call it, log G of S. So this is the number of different states in this space, you know. Right. If I pick one of these eigenstates for a given S, how many different ways can I make that total spin out of n spin a halves that are, and that's the degeneracy, and it just has the Shannon entropy minus n. Well, what I mean is just the logarithm of the degeneracy. Let me just write it out. It's a familiar formula. It's just the binomial entropy, or whatever you want to call it. So, right, if I have n spin a halves, and I want to add them up to make total spin S, say with fixed, for example, fixed SZ, particular value, there's all. There are.
That G of S just has a binomial. It's just written in terms of binomial.
Yes, I could write out an explicit formula of G of S in terms of the binomials. Let me do that, okay, if you want me to.
More recognized.
So this is, let me just, so this is the extensive part, right? This is only true to order n. There's corrections. Now let me get this right. So we have, well, it's the difference of two binomial coefficients. That's why I didn't write it out. Let me just get this right. So it's n choose n over 2 plus S well, I might not have this right. It's the difference of two adjacent binomial coefficients. You know, n choose something and n choose something different by 1. But that this correction is subextensive. The order n term, which is what I'm going to focus on, it is just the binomial coefficient. Yeah. Okay, so we have this degeneracy, which means each one of these states has that much entropy. Okay. Okay, so.
What do you mean by saying a state has that much entropy?
Well, sorry. Each energy level in the spectrum at a given S and a given energy has that much entropy, which is the logarithm in the number of states. Just the Boltzmann entropy. Logarithm of the number of states. Yeah. Okay. So. Right, so what do we have? We have a simple system. It's got two time scales, right? It's got this order 1 time scale and it's got this exponential and n time scale. Right? Order 1 moving in one well with either the magnetization down or the magnetization up, and then this exponentially larger time scale to tunnel from one to the
So
other.
I guess what you're meaning of the microcanonical entropy for fixed S.
Yeah,
Energy, so it
yeah.
would be a microcanonical
That would be a
ensemble.
microcanonical entropy. Yeah,
Yeah.
yeah. But let's just call it a degeneracy. And the logarithm of the degeneracy, then we avoid all these worries,
Yeah.
right? Although I'll keep saying entropy, I won't be able to stop. Because I'm going to do microcanonical thermodynamics or statistical mechanics just in a second, and then I'll do that. Okay. Okay. So what I'm going to do is I'm going to add a perturbation. Okay. So now add a perturbation to, and what I want to do is I want to break the SN symmetry and keep the global spin-flip symmetry. And what this will do is to lift all this degeneracy. So I want to lift all degeneracies. I want to cause thermalization, and I'll say what I mean by that. And it'll bring in another time scale associated with the thermalization. Yeah, in fact, on time scale, on a time scale much less than exponential of alpha n, which is the tunneling time, but much bigger than order 1. So I want to bring in an intermediate time scale between the two I've told you about
So
here.
If I start on the left side, I'm down, and then with exponential, I have to wait an exponential amount of time before I tunnel over to
up.
fix my states up, basically.
Yeah, that's right. So I want it to thermalize in this well on a time scale faster than it'll tunnel over to that well. Right. Okay. And so what I'm going to add is this. So H is equal to H naught plus, what I'm going to do is I'm just going to take this transverse field here and I'm going to make it slightly random. And I'm going to add to it a term that vanishes in the limit of large n. Sum I equals 1 to n, epsilon I, little si x. Okay? So what I've done is I've just, for each of these transverse fields on each spin, I'm making them slightly different from spin to spin. So that breaks this symmetry, right? And let's have this, these here are IID Gaussian mean 0 variance 1. Okay? So the probability of any degeneracy remaining due to two of these being equal is 0. Right? So that's what I mean. Lift all degeneracies with probability 1. Not absolutely. Okay. And this exponent here, in order to do this, okay, so I actually have two goals here. One is this, but we actually want to keep the thermodynamics of H. Actually, I already said that. In some sense, by saying this time scale is long compared to order 1, that has as a consequence the thermodynamics of H naught is not altered by this perturbation because it vanishes in the thermodynamic limit, really. So this perturbation, what it's going to do is it's going to change the dynamics of the system, but not the thermodynamics of the system. Okay? And I want this exponent p to be between 0 and a half in order for that to be true. Now, whether these are the correct bounds in order to achieve all these goals, that's, I think, a question that might need more care. So right now I'm actually getting to the part of this where I'm going to be making a bunch of assumptions. It's a reasonably simple situation. One reason I wanted to talk about this here today is because we have an audience of people who might actually be interested in taking what I'm going to tell you right now and making it, well, checking whether or not it's true, let's say. Let's put it that way. Checking whether or not it's true.
It's true, right?
What? Excuse me?
I said it must, if you think it's true, you have a strong belief that it's probably true, right?
Yeah. But it would be much more interesting to me if you proved me I was wrong than if you proved me I was right. Right? So that's why I want to encourage you to prove that I'm wrong.
About dynamics.
Okay.
So thermodynamics is a long time scale, it's a kind of intermediate time scale.
Well, no.
Okay.
No, because this system is integrable, it doesn't go to equilibrium ever. And so thermodynamics for this model doesn't happen, really. Like, I could start it in a non-equilibrium initial state with very peculiar spin correlations, and they'll live forever. And it's nothing like the Boltzmann distribution, right? So I'm actually, this is this system's dynamics. What I'm doing now is allowing it to do thermodynamics, right? Okay, and so what's this going to do? So what does this operator do, Si sub x? Okay, so this guy does not commute with the total spin, right? If you flip one spin, Sx, it doesn't commute with the total spin. So this, with random coefficients here, allows the total spin to change. So this allows S to change.
David,
In the unitary dynamics under the Hamiltonian, under the coherent time evolution given by quantum dynamics, S is no longer a good quantum number once I've done this because I've broken that symmetry. So this is no longer. So if I do that, and now I put a not equals, right? But that one is still equal. Okay?
David,
Yeah?
sticking this H naught before,
Yeah.
supposing you project on a subset of just K sites over there.
Yeah, that's one of the conservation laws. Yeah.
And each
Right.
subset,
Right, so I can just pick any number of spins. So let's say Sk, which is the total spin on K spins, and that commutes with the Hamiltonian. Right? So that's one way of representing all the symmetries of this guy here. Any subset of spins, the total spin, is an operator that commutes with H naught.
so a single site will have just
That's spin a half, right? But if I have two sites, I could put them with total spin 0, and they'll stay total spin 0 forever. I put them with total spin 1, they'll stay total spin 1 forever.
and that's no longer true.
That's no longer true here because, of course, I've broken that degeneracy, broken that symmetry. Exactly. Right. So this allows S to change, right? And it changes at a rate which is power law. So the time scale is a power law in n, bigger than 1, smaller than exponential. So we get this, right? I'm not going to argue that, but partly because I don't have an argument that's good enough to show to you guys. So it would be nice if that could be made a really solid argument. And so we need, right, and so this p less than a half, okay, right, okay, so I said over here the level spacing is of order 1, right? In order to get, and so what I want this perturbation to do is to cause these eigenstates here, which are spaced with a level spacing of order 1, to get strongly hybridized, right? And so I want the matrix element of this perturbation between my eigenstates over there to be bigger than 1, so that I strongly mix those states, right? And that's the p less than a half. I don't want this to be too small, right? So if p is less than a half, the norm of this operator goes to infinity. The norm of the total operator goes to infinity in the thermodynamic limit, and that gives those matrix elements big. You get strong breaking of the structure I have over there.
Coupling between the different
Right?
levels. Then.
Yeah. So what we want here, basically a quick way of saying it is, I want the mean field seen by each spin to be the same as in H naught. That's why I want P to be positive, so that my perturbation on the dynamics of each individual spin goes away in the thermodynamic limit, and the thermodynamics of the system thus can be unchanged. But I want the perturbation on the many-body system, which is the total operator, I want this operator to be large in the thermodynamic limit, right? And so this is saying the perturbation on a single spin is small and vanishes in the thermodynamic limit. This is saying the perturbation on the many-body system is large and becomes large in the thermodynamic limit. That's the essence of why I think these are the right inequalities, right? Okay. Okay, and so what we expect from this is thermalization. So we expect thermalization. And what I mean in this context by thermalization is the eigenstates of H and the long time states under e to the minus IHT. So either an eigenstate of H, or start with a non-eigenstate and just run to long time under the unitary time evolution, that these guys right, these go to thermal equilibrium. And the one fact about thermal equilibrium that I'm going to use is that the probability of the total spin being S is equal to, actually, let me not say. Yeah, that's right. S is no longer a good quantum number. Okay, so let me, yeah, okay, let me just say so. So this will be asymptotically equal to this, the degeneracy at S over the sum, say, S twiddle from the equilibrium value to n over 2 g of S. Okay, so at a given energy, since this depends on the energy, let me just say, before I say more about this formula, I just want to say a little bit about this thing on the bottom of the sum here.
And this is supposed to be.
That's what you have there.
Yeah. Can I try to say something first before I explain this and write it more clearly? Did you want to ask something, Joel? Or?
And this should be true for typical epsilons.
For almost all epsilon, yes. 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 Yeah.
Before you raise it, you pointed out that there is a tunneling amplitude of e to the minus alpha n, and based on that, states should be superpositions of the plus minus.
Eigenstates, yeah.
Do you know whether this applies to all the states, or would there be states which just live on one side versus another?
I think it's for all states. I don't, no, to have it be on one side and not the other, what you would need is a degeneracy.
There's a huge degeneracy also within each of the substates.
Okay, so for H naught, it's clearly not true. It's clearly always this. So this is a statement about H naught, and I think there's no way. This is just a one-dimensional dynamics, and you can't have any degeneracies. So the eigenstates will always be linear superpositions.
But
okay.
H naught has a high degeneracy, right?
Yeah, but
Within this degeneracy, would there be states for which the tunneling amplitude vanish?
no. So you can take a particular representation of this group, right, and take a given total spin, and the eigenstates will look like this problem, right? So we just have G copies of this problem here, right? And you're always going to have a splitting. So yeah, it doesn't happen here. And for this problem over here, I assume it'll only happen, the probability of it happening will be 0 because these epsilons are continuously distributed. Right? You can presumably fine-tune the epsilons so you have a pair of states where the tunneling amplitude happens to be 0, and you can make an eigenstate on one side or the other. But I think you would have to adjust one parameter in order to do that, in order to make this tunneling amplitude 0.
No, what I was referring to, but if you have a high degeneracy of these kind of mixed states, you may be able to produce states which live just on one side, the superposition of this kind of state.
I think for this problem, it's a one-dimensional problem, and it just can't happen. And it's just G copies of exactly the same problem, and they all have exactly the same spectrum. So it just can't happen. So I think that's simple. With this perturbation here, I'm sure if you adjust the epsilons, you can turn one of the tunneling amplitudes to 0 and have it happen. But it'll happen with probability 0. Okay, so we've got this picture here. Actually, let me draw it again. Okay, so what am I going to do? Let me just do it right here, next to it. Okay, so say we're at a given energy. In fact, let's say we're at the energy drawn right there. Okay, so we're at this energy. So here's energy, here's SZ. Right, and we're at this energy here. Okay. Now, we've got this entropy, which, I just erased it. So, G of S versus S, let's say log even, is it just looks like this. It's a decreasing function. It goes to 0 at n over 2. Okay, so the degeneracy goes to 0. It's exponentially large in n. So let's say 1 over n. Right, here it's log 2, and it goes to 0. Right? So the degeneracy is a monotonically decreasing function of s, vanishes at n over 2. So if we're at a given energy E, and the system thermalizes, so that its probability distribution is given by a microcanonical ensemble at this energy, then the most probable value of the total spin S will be the one with the maximum entropy, or maybe I should say the maximum degeneracy in H naught. And so that'll be the smallest value of S. So this is spin, not the entropy. This is the entropy along the vertical axis, right? Entropy, let's put a quotes on it to make everybody happy. And so for a given energy, we choose the value of the total spin that is minimal, that's consistent with that energy, and that's when this picture looks like this. Just touches. So we're in the, I'm assuming we're in the ferromagnetic phase. So it looks like this, right? So this is, and that's what I'm going to call S equilibrium. So S equilibrium, that drawing is bad because this and this should be equal and opposite, right? And this should be negative. So let's do it like that. Okay, right? And this, remember, this is at minus gamma S, the top of the barrier. Okay? So that's what I mean when I say S equilibrium, which is a function of the energy of the total system. They're both proportional to n. In fact, I can write S equilibrium over n as a function of E over n. Right? There's an intensive function there. That's the smallest possible total spin that's consistent with this energy. Right? If I tried to make the total spin smaller, it would just be inconsistent. Right? So it's gone to the maximum entropy state, which has the minimum total spin consistent with that energy. And the energy is negative. because we're in the ferromagnetic phase. Okay, so that's what's on the bottom of this. So here, the probability of having total spin S is proportional to the degeneracy of total spin S in H naught, normalized by the sum over all allowed values of total spin S, which run from the equilibrium value up to the maximum possible value. So this is just normalizing a probability distribution. Okay? Does that make sense now? Okay.
No, you're talking S is the whole system.
S is the total spin of the whole system.
So
That's
still,
right.
I mean, if you look locally and you first let the size of the system go to infinity, then you look at it as a function of time, you will be presumably in one or the other state.
Yes. Okay. So yes. Yes. Okay. So what I want to do, what I'm doing now, is I'm going to be talking about a finite system N, and I'm going to be focused on. So there's 3 time scales here. Now there is one of them, which is this precession on time scale 1. There's equilibration within this well to that probability distribution, which is really not. Right, this isn't the right picture, right? Because the energy stays the same. It's this guy that changes. So on the longer time scale, it thermalizes within the well, and then on this other time scale, it flips between wells. And I'm going to focus on this time scale. So the physics you're talking about is in the intermediate. So in the physics you're talking about is in this interval between these 2 scales here, right? But I'm going to focus on this scale today.
I thought you were focusing on the intermediate scale.
No, I want the intermediate scale so that the system thermalizes, right? So I need this to be there for the system to thermalize, and that's going to affect what happens on this scale.
Oh, okay.
Right? And I'm going to focus on this scale. Okay? And so how does the system, how does my cat flip from down to up, or up to down? It has to get across this barrier. Okay, so actually, something I should have said right at the beginning. What is thermalization about? The basic thing thermalization is about is, in a many-body system, is your system a reservoir that can serve as the reservoir to equilibrate its parts or not, right? And a system that is integrable, a system that is Anderson localized, does not do that. It does not go to equilibrium, whereas generic systems that don't have an excessive number of conservation laws that are sort of local operators do that, right? And so our system, right? So the idea is here, the system is a bath. It's equilibrating its parts, and I'm focusing on equilibrating one particular degree of freedom of the system, which is its total spin, right? Of course, there are lots of other degrees of freedom which are thermalizing as well, but I'm focusing on that one because that one is so important in the dynamics, okay? So how does the system get across this barrier? Okay, if the energy is high enough, one of its options is to, within this state here, go to the rare event of a large enough total spin that there isn't a barrier. And let me draw that in this picture. So if I go to a larger total spin, my picture might look like this. Right? And now with this energy, there's no barrier. So that's one way for the cat to flip, is for it to thermally excite itself to such a low entropy. So it's not exciting its energy, it's actually lowering its entropy, right? Because I'm talking about unitary time evolution, which is at constant energy. But this is a free energy barrier it has to get over. And there's 2 ways of getting over a free energy barrier. One is to raise the energy, and the other is to lower the entropy. And the unitary quantum dynamics only leaves the second option. And it can do that if it can change, in this model, if it can change the total spin, it can do that. And if it can change the total spin to be big enough so that the energy is above the top of the barrier, then it just goes across, right? And so this is thermally activated crossing a barrier by quantum unitary time evolution. So it's sort of a mixture of a quantum dynamics and a thermal dynamics. And we can exactly calculate what is the rate at which this, we can, the alpha, this alpha, okay, so let me just actually just write that here. Actually, you know what I should do? Since I should stop soon, right?
Yeah, just about 5 minutes or so.
Okay, so let me actually just summarize the whole story. I'll just do it right here.
Before you summarize, so what's the result now?
Well, I'm going to, since I'm out of time, I'm going to give my results. Okay, which is the following. Okay, so there's a phase diagram. So here's either the temperature or the energy along the vertical axis. Here's the ground state, which is 0 temperature, the ground state. So this is at finite n, and then take the limit to infinity after we do our calculations. And we're focusing, as I said earlier, on this, the time scale associated with the dynamics of the order parameter going from macroscopically up to macroscopically down. Okay, so of course we have TC, the thermodynamic phase transition. So up here, it's a paramagnet. There's no spontaneous symmetry breaking. It's not so interesting. And here, below here, it's a ferromagnet. And the eigenstates are Schrodinger cats. Okay?
You're talking about the H naught?
I'm talking about H, yeah. So this is for H with the perturbation. Well, this is true for H naught and H, what I've written so far. Okay. And now, within the ferromagnet, there's actually 2 phase transitions. And I'll call them TC2 and TC3, counting from above, so that's TC1. Okay. And they have so there's 2 distinctions here, one of which I was just alluding to. So TC2 is the transition from thermal cats. So these are systems where the system is a reservoir for itself, and it's a big enough reservoir so that you can take enough free energy out of the reservoir, which is really entropy, in order to get over the barrier without doing any quantum tunneling. Okay? And so that's why I call them thermal cats. They're Schrodinger cats, but they flip. They're quantum, but they flip quantum mechanically, not by the quantum process, but by thermally activating themselves over the barrier by lowering their entropy and not tunneling.
So I can treat that classically or semi-classically?
Semi-classically, right. And the rate of this, I can just write the formula down in terms of those probabilities. It just involves this entropy, right? You know, what's the probability of going to that S? It's just the entropy, you know, the binomial entropy, right? So that formula you can write down. And then down here, they are quantum cats. Meaning these guys here, when they flip, they don't go over the barrier. Actually, what they do is they lower their entropy a little bit, and then they tunnel. So there's an optimization of the most probable way of flipping, which is to go to a certain value of the total spin S and then tunnel, right? And so there's a saddle point condition to figure out how these guys tunnel. And so I call them quantum cats because they do tunnel through the barrier, right? They also thermally excite themselves up the barrier a ways before they go through. It's like when you go through the mountain, usually you drive up the mountain a little ways before you go into the tunnel, right? You don't just start in town drilling through the mountain, right? Because at the beginning the slope is easy, so it's better to just drive up before you tunnel, right? And they do the same thing, right? Okay, And then TC3, so these guys, SZ versus time, has an overdamped relaxation. Whereas here, SZ of t can oscillate.
They're still relaxed.
No, can oscillate forever in the limit of large n, although the period, of course, gets, okay. So there's two transitions. One is between the reservoir being big enough to get it over the barrier and not. The other one, let me just quickly say, and this is also a change in the spectrum, right? So what do the level statistics look like here? In H0, they're not interesting. In this problem with H, it's a real Hamiltonian. It's going to have GOE level statistics, right? And that's true throughout here. But there's a wrinkle in this lowest temperature phase, is its GOE level statistics of doublets, okay? So let me just, this particular phase here, which is the lowest temperature, just to get to the weak connection to random matrix theory here. And this will be my last thing, and then we can adjourn and have questions. So here is the spectrum of H, energy. And in this phase here, at the lowest temperatures, what does it look like? It looks like this. It's closely spaced doublets which have, so inter-doublet is GOE, and the level spacing is just given by, so delta goes as exponential, no, delta just goes as 1 over G of S equilibrium, right? So at equilibrium, the total spin is S equilibrium. This is the degeneracy. It's been lifted. And so all those levels are in an interval of order 1, and so the level spacing is roughly 1 over the degeneracy. Okay, so that's so this is the inter-doublet. Actually, this is the, everywhere in here the level spacing is given by this formula, but down in this lowest temperature phase, this formula applies to the spacing between doublets, and then intra-doublet delta. So this delta goes as exp minus alpha n, where this alpha, this is the rate for tunneling through the barrier. Okay? As you go to the ground state of this system, to 0 temperature, the entropy goes to 0, this degeneracy goes to 0, this level spacing gets big. This level spacing gets small because the barrier is getting high. And so this transition here is just when this exponential function of n and this exponential function of n exchange dominance. So it's when the logarithm of this, well, it's when either one of these or the other dominates at large n, right? So this is intra-doublet. Okay? And so here, what do these two states look like? They look like n plus or minus 1 over root 2 up plus or minus down. And I'll put a sub n on these, right? And so the doublet is just the positive and negative linear combination of two states. This state and this state are related by global spin flip. And so I can just make a linear combination of these two eigenstates. So these are eigenstates. If I make the equal amplitude linear combination of these two, it will just oscillate at the frequency given by the level spacing, and it'll do it forever. Right? That's the story down here. But once you're up here in these higher two phases of the ferromagnetic phase, it doesn't look like this. Two adjacent levels are not made out of the same up-ket and down-ket, right? So if we try to take two levels up in the higher temperature phase, we would have n and n plus 1. And I would write this construction here with an up sub n and an up sub n plus 1. But up sub n and up sub n plus 1 are orthogonal to each other. And so I can't make a linear combination out of two states, which is up, and then let it Rabi oscillate. I need an infinite number of states to do that. And it won't Rabi oscillate. It'll just relax. Right? And so that's what we believe happens over here. So there's two phase transitions, two dynamic phase transitions. They're only in the long-time dynamics. They reflect changes in the properties of the eigenstates also within the ferromagnetic phase. They are completely invisible to the thermodynamics because they only involve this energy scale, which is exponentially small in the size of the system, so it's irrelevant to the thermodynamics. It only happens in the mean field model. If I do short-range model in finite dimensions, you only get the higher temperature phase. Neither of these lower temperature phases happen because the barrier to flip is just making a domain wall, which is not an extensive amount of energy. So what's key to have this physics happen is that this barrier to go from one state to the other is an extensive barrier. And that only happens in mean field models. Okay, so sorry.